Welcome back, students. In this video, I would like to talk about unsigned versus signed arithmetic circuits. Okay, so let's get started. So far we have seen unsigned integers and we have seen signed integers, and the focus here will be on the 2's complement representation. This is the standard way of representing signed integers on computer systems today. So the focus will be on the 2's complement representation only. So I'm not going to talk about sign, magnitude, or the 1's complement representation. Now for unsigned integers are 0 extended. If you have an unsigned integer, you always extend it with zeros. If you would like to extend it, let us say from 4 bits to 6 bits, you extend it with zeros. If you have a signed integer, on the other hand, you use sign extension. So the signed integers are sign extended. For example, if you have x, which is a 4-bit unsigned integer, then the range will be from 0 to 15, where 15 is equal to 2 to the power 4 minus 1, if you have a 4 bits, because we only have 4 bits. If you have y, which is a signed integer, then the range will be from -8 to +7. So 7 here is equal to 2 to the power 3 minus 1. That's the range of values that you can represent if y is signed. Now, for example, if x is equal to 1101 in binary, then the decimal value, when you convert it from binary to decimal, will be equal to 13. On the other hand, if y is equal to 1101, it has exactly the same bits, but y is signed, then the decimal value will be -3. So even though the binary representation is the same, the decimal value is different because y is signed. Notice that the most significant bit here has the weight of -8. So this is the sign bit that has -8, -8 plus 5. It's difficult to write here on the screen. -8 plus 5 is equal to -3. So for this reason, the decimal value is -3. Whereas if it is unsigned, it will be 8 plus 5. It will be equal to 13. So now, let me. Okay, so now if I would like to extend x from 4 bits to 6 bits, then I'm going to add 2 zeros to the left. This is called zero extension. So x is still 13 with 0 extension. So 0 extension does not change the value of an unsigned integer. On the other hand, if I would like to extend y and y is signed, then I'm going to use sign extension. So since the sign of y is negative, I have to extend it with ones. So the value of y will still be -3. So sign extension does not change the value of y. It is still -3. Whereas if I do zero extension for y, then I'm going to change its value to 13. So for this reason, we don't use zero extension when we are dealing with signed integers. We use sign extension. Notice that the most significant bit now is the sign bit after extending y to 6 bits. So this is actually my most significant bit here, and it will have the weight, which is -32. And the remaining bits will be plus 29. If you convert 11101, it will be 29 in decimal. The most significant bit now is the sign bit is -32. So minus negative. So negative 32 plus 29 will give me negative 3. So you can see that sign extension does not change the value of a signed integer. Now, if I would like to design a circuit that computes s is equal to x plus y, and x and y are unsigned integers, then the value of x and y can be from 0 to 15. This is the range of values of x and y. Now, when you add x plus y, the maximum can be equal to 30. So the maximum will be equal to 15 plus 15. This is the maximum of x, and this is the maximum of y. So the maximum sum will be equal to 30. And therefore, you need 5 bits to compute the sum. Okay? You can do this with a 4-bit adder. So this is a 4-bit adder for adding x plus y. Notice that the most significant bit here, S4, is the final output carry, which is C4. So we use the carry as the most significant bit when we are adding unsigned integers. So the final sum consists of 5 bits, okay, from S0 to S4. So these are 5 bits. So the 5 bits will give you the exact sum of the unsigned integers. But what if I would like to add signed integers? So suppose I would like to compute s is equal to x plus y, but x and y are signed. So the range of x and y will be from negative 8 to plus 7. So if I would like to do, okay, this sign addition, I have to do sign extension. So if you look at the minimum, it will be negative 8 plus negative 8, which is negative 16. This will be the minimum of x plus y. And if you look at the maximum, it is plus 7 plus plus 7. It will give you plus 14. So this is the maximum signed value. So we have from negative 16 to plus 14. So s must be 5 bits. Okay, so we need a 5-bit adder to calculate s is equal to x plus y. Notice that x and y are sign extended. Notice that x3 is replicated and y3 is replicated to calculate the most significant bit, S4. S4 is not equal to C4. Why? Because this is x and y are not unsigned, they are signed integers, and therefore you must extend x and y, and then we have to add them to calculate the correct bit, the correct S4. So this is why we use sign extension to calculate the most significant bit S4, and we need an extra full adder to calculate the most significant bit S4. So remember that in the case of signed addition, we cannot say that S4 is equal to C4 because we are dealing with signed integers. The most significant bits must be sign extended, and they must be added using one extra full adder as indicated here. Okay. So that's my 5-bit sum. If I use a 4-bit adder to calculate the sum, I might get overflow. So this is why we are using here a 5-bit adder. We are using 5 full adders to compute the exact sum. How about subtraction? Suppose I would like to design a circuit that calculates s is equal to x minus y, where x and y are unsigned. So the range is from 0 to 15 because x and y are unsigned integers. How do I calculate x minus y? We can always convert subtraction into addition to the 2's complement. So we can say that x minus y is x plus the 2's complement of y, and the 2's complement of y is y prime plus 1. So I'm doing here addition to the 2's complement. So I have converted this subtraction minus y into plus the 2's complement of y. And the 2's complement of y is the 1's complement of y plus 1, which is y prime plus 1. Now, what is the minimum value of s and what's the maximum? The minimum is that when x is equal to 0 and y is equal to 15. So the minimum s is equal to negative 15, whereas the maximum s is equal to plus 15. Now, even though x and y are unsigned, but when you subtract, you can get a negative sum. So the sum can be negative and it can be positive, even though x and y are unsigned. So now if I would like to represent the range from negative 15 to plus 15, I need 5 bits. So s must be equal to, must be 5 bits. So let us design here a circuit that can calculate s is equal to x minus y. Here's a circuit that can compute s is equal to x minus y. Notice that x and y must be extended because x and y are unsigned. We can use 0 extension. Notice that y is inverted. Notice these inverters here. So the inverter here is to calculate the 1's complement of y. And here we have C0 is equal to 1. This will calculate, okay, the 2's complement of y. So the 2's complement of y is equal to y prime plus 1. Now, when you complement, okay, 0, you get a 1 here. So x is 0 extended, y is 0 extended and inverted. So here we have a 1, which is just the complement of 0. So this will calculate the 5-bit sum S4 down to S0, and this is x minus y, where x and y are unsigned. Do we really need this full adder to calculate here, okay, 0 plus 1 plus C4? Well, if I would like to calculate 0 plus 1, okay, remember that this one is 0 prime because we are complementing y. So 0 plus 1 is just equal to 1. It does not really need a full adder to calculate 0 plus 1. It is just 1 plus C4. But what is 1 plus C4? 1 plus C4 is equal to C4 prime. So we can, why it is C4 prime? Because if C4 equal to 0, we get 1. And if C4 is equal to 1, we got 0 and a carry. But the final carry here, we don't really need actually an extra carry. So we only get a 0. So if C4 is equal to 0, we get a 1. If C4 is equal to 1, we get a 0. So we can replace this full adder here with an inverter. There is no need for a C5, an extra output carry, because we know that the exact sum can be represented with 5 bits. So you can see that the most significant bit, okay, the most significant full adder can be replaced simply with an inverter. And this is the circuit that calculates the unsigned subtraction s is equal to x minus y, where x and y are unsigned. If I would like to do signed subtraction, okay, I would like to design a circuit that computes s is equal to x minus y, where x and y are signed. The first question that comes to my mind is that what is the range, okay, for x and y and s? The range for x, the range of y will be from negative 8 to plus 7. The range for the sum will be minus So what is the minimum s and what's the maximum s? The minimum s will be -8 for x and +7 for y. So -8 minus +7 will give me -15. And the maximum will be +7 minus -8 will give me +15. So what I need is that I need to be able to represent this range from -15 to +15. And to represent this range, we need s to be 5 bits because it cannot be represented with 4 bits. With 4 bits, you can go from -8 to +7. But with 5 bits, you can go from -16 to +15, and we can represent the full range for s. So for this reason, we should have 5 bits for s, otherwise we might get an overflow. If we use 4 bits, you will get overflow. So for this reason, we are using 5 bits for this sum s. So here's a circuit that calculates s is equal to x minus y. Notice that x is sign extended, the same thing for y. Notice that y is inverted because we would like to calculate x plus y prime plus 1. That's -y. It's actually the 2's complement of y. So we are inverting y and we are adding here +1. So C0, my input carry C0 is equal to 1. So we are using 5 full adders to calculate the sum S4, S3, all the way down here to S0. This is my 5-bit sum. And we are replicating, or we are extending the sign bits, okay, x3 and y3. Notice that y3 is inverted and replicated, okay? That's a y3. We are actually inverting it and we are replicating it. And the sum now will be x minus y, where x and y are signed integers. Next, let us design a circuit that calculates 2 times x plus y. So how do we calculate 2 times x? Okay, so x here and y are unsigned integers. So how do we calculate 2 times x? We can calculate 2 times x with shifting. Okay, so we can shift x to the left by 1 bit. This will give me 2 times x. So 2 times x is x shifted to the left by 1 bit. So what we need to do is that we need to shift x to the left by 1 bit, and then we can add to it y. So what is the maximum value for s? Now, if x and y are unsigned integers, the maximum value of x and y are 15. So the range is from 0 to 15. So we say that the maximum value of s is 2 times 15 plus 15. This will give me 45. Now, 45 cannot be represented with 4 bits or 5 bits. So we need 6 bits to represent the final sum s. So 6 bits are needed to represent s. So now I need to design a circuit that can produce 6 bits for s. It has to shift x and then add to it y. Here's a circuit. Notice that x is shifted to the left, and this is y. So y consists from y3, y2, y1, y0. I can use 0 extension here for y. 0 extension for y because y is unsigned. And now when I shift x to the left, then I will add x0 plus y1. Now y0 will be added plus 0 because when you shift to the left, you insert a 0 from the right. So y0, which is the least significant bit of y, will be added with 0. Now we don't need a full adder to add y0 plus 0, so we can say that the least significant bit of s, which is s0, is nothing but y0. So this can be connected with a single wire, and there is no need for a full adder to add +0. So we can start adding x0 plus y1, x1 plus y2, and so on. Now notice that because here we have C1 is equal to 0, I can replace this full adder with a half adder. In other words, we can simplify even this circuit. And finally, the final output carry here, which is C5, is the most significant bit of my sum. So now my sum will consist of 6 bits, S5 down to S0, and the most significant bit S5 is C5, which is the output carry. It is C5 because X and Y are unsigned integers. Suppose I would like to do the same thing, but X and Y are signed. This is shown in the next slide. So let us repeat this. Design a circuit that will compute S is equal to 2 times X plus Y using full adders, but now X and Y are signed integers. These are 4-bit signed integers, so the range is from -8 to +7. So in order to do something like this, again, I'm going to shift X and I'm going to shift X to multiply it by 2. And I'm going to do sign extension for X and Y because these are signed integers. Now the range, you can actually say what is the minimum S and what's the maximum S. So the minimum for S will be 2 times -8 plus -8 because this is the minimum for X and the minimum for Y. So you will get -24. That's the minimum value of S. What's the maximum value of S? It will be 2 times +7 plus 7. This will give me +21. Now, in order to represent the range -24 to +21, you need S to be 6 bits. So you need 6 bits for S. If you use less than 6 bits, you might get overflow. So to avoid getting overflow and to compute the exact sum S, we need 6 bits for S. Okay. So this is S. So now I would like to design a circuit that does this calculation 2 times X plus Y. The trick is to use shifting. So to multiply X by 2, I need to shift X to the left by 1 bit. So here's my circuit. So when I shift X to the left, then I'm going to add X0 plus Y1. I'm going to add X1 plus Y2 and so on. This Y0 will be added to 0. Okay, so let me write here +0. Okay, because I'm adding here +0. Okay, there is no need for an adder. There is no need for a full adder to add this. Also, this full adder, because C1 is equal to 0, this full adder can be replaced with a half adder and can be simplified. Finally, you can see that okay, how SSX3 is replicated because this is called sign extension. So we are replicating the sign bit X3. And notice that Y3 is also replicated. So this is sign extension. So we are doing sign extension for X3 and so for X and for Y. So X3 is replicated and Y3 is replicated. And the final sum consists of 6 bits. S5 down to S0. Now, suppose I would like to design a circuit that can compute unsigned less than. So I would like to compare X with Y. X and Y are unsigned integers. And I would like to output less than. Now, we have already seen a magnitude comparator. Okay, so the magnitude comparator can compare two unsigned integers, X and Y, and it can output less than. It can also output equality and can also output greater than. That's the magnitude comparator that we have seen in a previous lecture. So here I would like to design a circuit. Okay, I'm going to design a circuit that can output less than differently. So in order to check if x is less than y, I can calculate x minus y. So I'm going to use a circuit that calculates x minus y. So if x minus y is negative, then it means that x is less than y. That's another way to check that if x is less than y. If I would like to check for equality, x is equal to y, then I can check if x minus y is equal to 0. So we can use the same circuit that we have used before to calculate x minus y. So we can calculate the difference x minus y, we can do subtraction, and then we can check the true sign of x minus y. If the sign bit is negative, it indicates that x minus y is negative and x is less than y. So we're going to use unsigned subtraction because x and y are unsigned, and we are going to check the sign bit of the result. We already have designed a circuit that calculates x minus y. So this is a circuit, okay, that we have seen in a previous slide that calculates x minus y, and you can see that you can see that here y is inverted, okay, so this is x plus y prime plus 1. You can see that C0 is equal to 1. So we're calculating x plus the 2's complement of y. And notice that we are detecting here, okay, we are looking at the sign bit. So the sign bit here, S4, is the sign bit, is just, we are complementing C4. So here, the most significant bit, okay, of the sum here, so of S. So here S is equal to x minus y, and the most significant bit indicates the sign of x minus y. So if this sign is equal to 1, it indicates that x is less than y. It indicates that x minus y is negative, and therefore x is less than y. So the sign bit is just the complement of C4. Now, if C4 is equal to 1, it indicates that it is greater than or equal. So if it is not less than, it will be greater than or equal. If you would like to check for equality, you have to check the sum bits S0, S1, S2, and S3. If all of them are zeros, it indicates that the difference is equal to 0, and therefore we can use a NOR gate, okay, that will output 1 if all its inputs are zeros. So if the difference x minus y equal to 0, then the output of this NOR gate will be equal to 1, and that will check for equality. So this is how we can design a circuit that can detect if it is less than based on the sign bit S4, and it can also detect equality. So the trick is to calculate x minus y. And already we have designed a circuit that can calculate x minus y, and we can look at the sign bit of x minus y to check if it is less than. Okay. Now let us repeat this, but we would like to design a circuit that can compare x and y, where x and y are signed. So if x and y are signed, okay, we need to design a circuit that can calculate x minus y, but we have to do sign extension. Already we have designed a circuit that can calculate x minus y when x and y are signed. So here is the circuit that can calculate x minus y. Notice that y is inverted. So this is, we are calculating x plus y prime plus 1. That's actually x plus the 2's complement of y. And the output will be x minus y. Notice that we are using sign extension for x and for y. So we are extending here x3. we are extending y3 prime, which is just the complement of y3, and the most significant bit here, which is S4, is the sign bit, is the true sign of x minus y. So if this sign bit is equal to 1, it indicates that x minus y is negative, which means that x is less than y. So the difference between this circuit and the previous one that we have seen in the previous slide is that we have to use sign extension, and we need an extra full adder here to compute the most significant bit S4 that will indicate will be the true sign of x minus y. For equality, we can just use a NOR gate that will output 1 if all the sum bits are all zeros. Okay, so that's this. So the NOR gate will check here for equality, and it means that x is equal to y if x minus y is 0. Okay. Now we can design actually more circuits. For example, I can design a circuit that can calculate the sum of 3 numbers, of 3 unsigned integers, x, y, and z. Now suppose that x, y, and z are unsigned integers, then their range will be from 0 to 15. And therefore, if you look at the maximum value of s, it will be 15 plus 15 plus 15, which is 45. And since 45 is greater than 31, it cannot be represented with 5 bits. You need 6 bits to represent the sum s. Okay, 6 bits are needed, because if you use only 5 bits, then the maximum will be 31. If you use 4 bits, the maximum will be 15. So you need 6 bits to represent a sum which is greater than 31, and this can actually represent the maximum sum, which is 45. So you need 6 bits for that. So in order to design such a circuit, I can use 2 adders. Okay, so the first adder is a 4-bit adder that will calculate x plus y. So I can use a 4-bit adder to calculate x plus y. So this 4-bit adder is going to produce a temporary sum, which is t. So notice that t here will consist of 5 bits. So the 4-bit adder is going to produce the sum, which is t3 down to 0. And the carry out will be t5. So this will be an extra bit, okay, for the sum. So now the sum will consist of 5 bits. The 4-bit sum plus the carry out. So these are 5 bits in total. Now z is 0 extended to become 5 bits, and the second adder will be a 5-bit adder that will add t4 down to 0 with z. Okay, so the temporary sum. So t here is the sum of x plus y, and then we take this t and we add it to z. Now z must be 0 extended to 5 bits because z is unsigned. So we use a 5-bit adder is going to produce a 5-bit sum and a carry, but the carry becomes bit 6. So now in total we have a 6-bit unsigned sum. So we use a 4-bit adder and we use a 5-bit adder. In total, we have inside the 4-bit adder, inside this adder here, which is the 4-bit adder, which is shown here, we have 4 full adders. Inside the 5-bit adder, we are using, inside this block, we have 5 full adders. So the block here consists of multiple full adders, but these full adders are connected. This is a ripple carry adder consisting of multiple full adders, but I'm drawing them as blocks, okay, to simplify the drawing. So now we are going to a higher level, okay, designing a larger circuit using 4-bit adder and 5-bit adder, but these adders are made out of full adders. Okay, so This is the design of a circuit that calculates the unsigned sum S is equal to X plus Y plus Z. Next, let us design a circuit that can calculate the sum W plus X minus Y minus Z. Now, in this circuit, okay, my inputs are signed integers. So the range is from -8 to +7. So we can always look at what is the minimum and what is the maximum and what is the range and how many bits do I need to represent the final sum. Now, the nice thing, well, in this example, to calculate W plus X minus Y minus Z, I can put between parentheses minus between parentheses Y plus Z. So I can rewrite my sum like this. So I can calculate W plus X using one adder, and then minus between parentheses Y plus Z can be calculated with another adder. So I need one adder for this addition, W plus X. I need another adder to calculate Y plus Z. And I need a third adder to calculate this subtraction here. So I can convert subtraction into addition to the 2's complement. So I need 3 adders in total. Now you can say, how many bits do you need? When you add W plus X and W and X are 4 bits, the exact sum will be 5 bits. The same thing when you add Y plus Z, then the exact sum will be 5 bits. And when you subtract, you will get 6 bits in total. You can also look at the range of values and you can see that you need 6 bits to represent the exact final sum. So let us design such a circuit. This is shown here. So I'm using here a 5-bit adder to calculate W plus X. Now notice that W and X are sign extended. You can see that the sign bit here is replicated. You can see that W3 is replicated, X3 is replicated, Y3 is replicated, and Z3 is also replicated. This is sign extension. So bit 3 is the sign bit and it's replicated. So we are extending the numbers W, X, Y, Z from 4 bits to 5 bits. And I'm using a 5-bit adder here. These are 5-bit adders to calculate the intermediate sums. So I'm calling here W plus X, I'm calling it U. So the output here is U. And the output here is V. So U consists of, here is U. U consists of 5 bits, 4 down to 0, and the same thing for V. V also consists of 5 bits. So these 5-bit adders are going to produce a 5-bit sum. So the bits are numbered from 4 down to 0. Now to calculate the final difference, this minus, I need to add U plus V prime plus 1. So I'm using an inverter here to invert all the bits of V. So this is V prime, and this is the plus 1. But I would like to produce a 6-bit sum at the end. So what I have to do in order to produce this 6-bit sum, I have to do sign extension for U4. This is now, you can see this is sign extension. And I have to sign extend here V prime 4. So first I'm going to invert V, and then I'm going to do sign extension. And then I can add. So now my inputs are 6 bits, and this 6-bit adder is going to produce a 6-bit sum. And the sum here is signed. So this is sign extension, and we're producing a signed result. So this is why we use sign extension when we are dealing with signed integers. Now my final example will be about calculating the absolute difference. I really would like to calculate the absolute value of X minus Y, where X and Y are signed integers. So to design a circuit that calculates the absolute difference of X minus Y, first I need to calculate x minus y, and then I can check. So first I need a circuit that calculates x minus y. Already we have designed this circuit before, so that's easy. We can just add x plus the 2's complement of y, and then we can look at the difference. If x minus y is positive, then this is the final value. If it is negative, we have to take the 2's complement. We have to take the negative of the result to calculate the positive value, because this is the absolute value of x minus y. So you will say that how many bits do I need for a? Well, the maximum value for the absolute value, the maximum value of a, which is the absolute difference, you say what is the minimum value of what is the minimum value of x is -8 minus +7. This will give me -15. So the absolute value of -15 is 15, and since it is 15, it can never exceed 15. Then you need 4 bits, okay, because you can represent here any number between 0 and 15. 4 bits will be sufficient for the absolute difference. So first I need to calculate x minus y, but since x and y here, okay, are signed, I need to use a 5-bit adder to produce the difference. So I'm going to use a 5-bit adder to calculate x minus y. So x minus y here, okay, can be okay, so I need to use here sign extension to extend x and y, because x and y are signed, and I'm going to invert y and add +1. So you can see this inverter is going to invert all the bits of y. So we use sign extension. You can see that actually x and y are sign extended. I'm using a 5-bit adder to produce the correct sign bit, okay? Because if I use a 4-bit adder, I might get overflow. So if you look at the range of values of x minus y, then you see that in this range, okay, you need 5 bits. 4 bits are not really sufficient. You need a 5-bit adder to calculate x minus y. But then you can look at the sign bit, which is S4. Now, if the sign bit is 0, it indicates that the difference is positive. If the sign bit is 1, it indicates that the difference is negative. So what I really need to do is that I need to calculate the absolute value. So if S4 equal to 0, okay, when you XOR all the bits here, S3 down to 0, with 0, you get S. If S4 is equal to 1 and you XOR with 1, you get S prime. Now, if S4 is equal to 0, then the carry in will be equal to 0. If S4 is equal to 1, then the carry in will be equal to 1. So in other words, okay, if already we have, okay, the difference is positive and S4 is equal to 0, we just pass here S plus 0. So basically we get here the absolute difference is equal to S. However, if S is negative, so S4 is equal to 1, I'm going to actually calculate here S prime plus 1. So this will be the 2's complement, okay? The 2's complement of S prime. So the negative of a negative is positive. So you get here the absolute value of S when S is negative, okay? So you get actually either S or you get minus S, which is equal to the absolute value of X, the absolute value of S if S is negative. So if S is positive, you get S. If S is negative, you get the negative of S to convert it to positive, and this is the absolute value. So to calculate the negative, I have to invert S and then add 1. This will be the 2's complement of S. So what this 4-bit incrementer does, it calculates the 2's complement of S in case S is negative. What this XOR gate does, it calculates the ones complement of S, if S4 is equal to 1, if S is negative, it calculates the ones complement, and then you add 1 here as the carry in to calculate the 2's complement. We already have seen how to implement a 4-bit incrementer in a previous presentation. This is shown here. This is the design of the incrementer. I'm drawing it here as a block. Okay, you can see that actually is my incrementer as a block. But really inside this incrementer, we have half adders because there is only one input X, and I would like to increment it by Cn. Cn here is my input carry. We can just use half adders to increment the input X. And these half adders can be implemented with XOR gate and an AND gate to propagate the carries. So this is how the incrementer is implemented from the inside. It's implemented as just half adders. That's it about this presentation. Thank you for watching.